Okay, let's take a look at our fourth installment for Lecture 1. And at this point, we've looked at subatomic parts. We've made our atoms starting at the nucleus. We've looked at our orbitals where we can put electrons. And now we want to start putting electrons into our orbitals because it's the electrons on the atoms that do our bonding and also are most involved when we're doing reactions. So putting electrons into orbitals is a very important aspect of building our atoms, and for that reason this is actually going to be a fairly long part of Lecture 1. Now when we look at electrons, one of the things we first saw back in 1921 was that electrons can be split with a magnetic field. And this is one of the things that led to this idea of the electron spin quantum number m sub s. When a beam of hydrogen atoms, each with a single electron on them, were passed through a magnetic field, what we saw is that the atoms actually deflected in two opposite directions. And since the hydrogen atom has only one electron, the deflection was caused by that electron and how it interacted with the external magnetic field. If we think about what an electron is doing, it turns out that it's actually spinning in space, and because it's charged and spinning, that gives it a magnetic field that is dependent on the direction of the spin. And so that magnetic field develops a direction based on the direction of that spin. So here we can kind of see the experiment there as far as what happened. We have a source of hydrogen atoms here. We pass it through. This is a very rudimentary diagram. We pass it through some type of focusing element there, and we get a single beam of atoms. We pass it through a set of magnets here with a north and south pole, and what we find is that the beams of the hydrogen atoms actually splits, with one of those beams corresponding to an attractive force with a spin of -1/2 and one a repulsive force with a spin of +1/2. And so the 1/2 value actually comes to help some of the math work out for some of the more complex quantum mechanics involved, but the plus and the minus indicates the opposite magnetic fields. So in order to show how electrons go into our orbitals, we use something that is called spin notation. And again, this helps us arrange our electrons in our orbitals using something that's called electron configurations or electron diagrams. These are not the same thing, but we do use them for the same thing. We use them to show where electrons are as far as what orbitals they're in. I don't think that was supposed to come up quite so quick. There we go. So if we have an orbital diagram, each subshell is labeled and each orbital is noted by a square or a line. I tend to use a line when I'm drawing. Textbooks tend to use squares. And so this would be an orbital diagram here to the right. And so for a hydrogen atom, we only have a single electron. It goes into the 1s orbital. And again, for that 1, that's our n value. And our s, that means that L is equal to 0. So we call that a 1s orbital. We have our 1 electron. Notice that it's just a single-headed arrow right there. And we would say that that one is spin up. There's no reason we couldn't put it in as a spin down. We just tend to start with spin up for whatever reason. So that would be our orbital diagram for hydrogen. Now, if we want to do an electron configuration, we have this right here where we have our orbital listed, the 1s, and then in a superscript, we write the number of electrons that are present in that orbital. And so we would read that as 1s1 is how we would say that. When we're putting our electrons into the into the orbitals, we have to use something called the Aufbau Principle, right? So we have to follow the Aufbau Principle. And what that means is that when we are putting electrons into those orbitals, we can't just place them anywhere we want in any order. Electrons fill in a very specific, important order, and they always go into the lowest energy orbital available. Okay, remember our energy is determined primarily by our n value. So n equals 1 has lower energy than n equals 2, which has lower energy than n equals 3, etc. as it goes up. We do start running into some complicating factors that we'll talk about a little bit later, but for now, that's what we want to accomplish there. When we're looking at the individual shells, if we are within a single shell, so if we're within the n equals 2 shell, we know that we have 2 s orbitals and 2 p orbitals. The s is going to be lower in energy than the p. And so for lithium, which has 3 electrons there, we can write an electron configuration as 1s2, 2s1. Notice that if you sum up the numbers here as our subscripts, we should get the number of electrons that we're putting in there. So that should equal the atomic number that we see in the periodic table. So there we go. And when electrons are in their lowest possible energy arrangement, like we have here for lithium, we say that this is the ground state. Okay, so when we refer to an atom in its ground state, that means that all of the electrons are in their lowest possible energy. Now, we may ask ourselves, why couldn't we just put all 3 of these electrons here into the 1s? Well, that's because each orbital here can only hold 2 electrons. That corresponds to that spin up and spin down for m sub s. And we'll talk a little bit about that later. But once I have filled an orbital, then I have to go to the next highest energy orbital and fill that one in. So we have the Aufbau principle that indicates energy level. We're always going to fill in the lowest possible energy level. The Pauli exclusion principle is another principle that we have to follow when filling in electrons. And this says that no 2 electrons in an atom can share the same set of 4 quantum numbers. This is a little bit like saying that no house can have the exact same address. Okay, we have lots of different parts of addresses for our homes, and many homes share portions of an address, but they don't have the exact same address. For example, any home within your home city would share the same town. Any homes on your street would share the same town and the same street, but then your house has a house number on it, and so your house would have a very specific street number, street name, and city. Okay, and so your house has a specific set of address numbers. In that same sense, electrons have a very, not a very unique, just a unique set of quantum numbers, that set of 4 quantum numbers, n, l, m sub l, and m sub s. And because of that spin limitation where we have only 2 possible values of m sub s, that means that an orbital is defined by the first 3 quantum numbers, and that 4th quantum number, m sub l, means that we can only put 2 electrons in to that one orbital sharing the first 3 quantum numbers, because once we have an orbital with 1 electron spin up and 1 electron spin down, we have exhausted that set of first 3 quantum numbers in there. So we have to change something. So for an example here with helium, we have a 1s2 electron configuration. It has an orbital diagram of a spin up and a spin down. We have a set of quantum numbers where n for these is equal to 1, because n is equal to 1 there. We have an s orbital, so L is equal to 0. Because L is equal to 0, m sub L can also be equal to 0. And then the m sub s can only be spin up and spin down. And at that point, I've exhausted all of the possible quantum numbers for that arrangement. And there we go. So we can have an n equal to 1, L equal to 0 for both, and M sub L equal to 0 for both, but they have to differ somewhere, and the only place these two can differ is in the M sub S, plus 1/2, minus 1/2. Since those are the only two allowed values for M sub S, then that orbital is done, and there would be no way to put in another electron with a different set of 4 quantum numbers. I hope that makes sense to you. If it doesn't and it's confusing, please make sure that you come see me. Think about the house address. Sometimes that helps. Another rule, we just have lots of principles and rules for filling up our electrons here. So Hund's rule states that when we're filling degenerate orbitals, and that's a word that you may not have seen, or you've seen it in a different context, but when we're filling degenerate orbitals, electrons will go in as single electrons with parallel spins before they begin to pair up. So what a degenerate electron is it means that you have orbitals with the same energy. And I apologize for my handwriting. It's a little difficult on a tablet, but that means that these orbitals have the exact same energy, and there's nothing to differentiate one from filling up before the other. And so if that occurs, and it does occur, and with p orbitals and d orbitals and anything above that, the electrons will go in as single electrons with parallel spins, meaning they'll all go in as a single electron with spin up or spin down before those electrons begin to pair up. Now, the reason they go in as singles before pairing up is because there's a repulsive interaction between electrons in the same orbital. Remember, your electrons have a charge. They have a negative charge, and negative charges, or similar charges, always repel each other, and so that's a repulsive interaction. And repulsive interactions raise the energy of a system. Mother Nature wants the energies to be as low as possible. We want atoms to be in that ground state, and so we do as much as we can to keep the energy low. By putting electrons into different orbitals, we remove the possibility of that repulsive interaction. Now, sometimes it can't be helped, and we'll see that here in just a little bit. So for carbon, we have an electron configuration for carbon. Carbon has 6 electrons, and we see that because it has an atomic number of 6. That means it has 6 protons in the nucleus. That also means it must have 6 electrons to counteract the 6 protons. For as far as charges, we have 6 positive charges from the protons, 6 negative charges from the electrons, and that gives us a neutral charge. So our electron configuration, when we're filling up with 6 electrons, the first 2 go into the 1s, the next 2 go into the 2s, and the next 2 go into the 2p. Okay, notice that we have a p orbital here. We have 3 possible orientations for a p orbital because it has 3 m sub L values, an m sub L value of -1, 0, and +1. And so we have 3 degenerate orbitals. They have the exact same energy. Each of these orbitals can hold 2, which means a p orbital can hold 6 electrons. Now, because it can hold 6 doesn't mean that it has to hold 6. It's a little bit like having a 5-liter bucket. If you have a 5-liter bucket, you don't have to put 5 liters of water in it. You can put 2 liters of water in it. It holds 2 just fine, or 3 or 4. Okay? It can hold up to 5, but it can have anything less than that. Orbitals are a little bit like that as well. Okay, just because the p orbitals can hold 6 doesn't mean that we have to put 6 in there. Okay, here we only have 2 electrons to put into the 2p, and so that's all that goes in there. But let's take a look at our orbital diagram. So the first 2 electrons go into that 1s, the next 2 electrons go into that 2s, and now we're left with 2 electrons into the 2p. Notice that we did not do that. We did not pair up those electrons in the same orbital. And that's because that's a higher energy than putting them like that. Okay, because putting them in this exact same orbital would have added a repulsive interaction and would have raised the energy of the atom. By keeping them in separate orbitals with parallel spins, notice these are both spin up, then we've kept the energy of the atom low. Now we get into a couple of concepts that we're not going to look at extensively, but you might want to read about them. And these are effects of things called penetration and shielding. And as you start to get into some of the upper level orbitals, the order in which these orbitals fill isn't always what's expected. And the idea of well, we'll see some graphs here with penetration and shielding. But what happens is your outer sublevels within a level, an n level, begin to go up in energy. So your d orbitals are sometimes higher in energy than you would expect, and the s and the p's might be a little bit lower than what you would expect. And sometimes these two things can begin to overlap between n levels, and it changes the order in which the orbitals fill up. Okay, so let's take a look at what effect that has. So we start with our 1s, that's the lowest energy, and then we go to the 2s, that's fine, that's what we expect, and an s is lower than a p, so the next thing we fill in are the 2p orbitals, the 3 of them that are there. Then we move to the 3s, so the 3s comes next, that's great. And then we have the 3p orbitals, perfect, the p comes right after the s, and so that's great. And then if we look at what's the next lowest, we see that we've got a 4s here, even though the n equals 3 level has 3d orbitals. Well, 3 is less than 4, so why does the 4 fill in before? Why does the 4s fill in before the 3ds? Again, it has to do with this idea of penetration and shielding. Shielding drives the level of these 3ds up a little bit, and penetration allows the 4s to come down in energy a little bit, so much so that it crosses the energy barrier. And so after we fill our 3p, the next two electrons are going to go in the 4s, and then any after that begin to fill in the 3d, and then the 4p, and then the 5s, and then the 4d, and things start to bounce around quite a bit. It looks quite confusing, but the nice thing is that the periodic table is going to tell us exactly what order we need to fill things in. Okay, before we do that, we want to look at something that's called noble gas notation when we're writing electron configurations. Remember, an electron configuration is where we write down the n value, the orbital that's being filled in, and the number of electrons that are in there. So 1s2, 2s2, 2p3, or whatever. Okay, so if we look at an example for aluminum. So aluminum, if we look at the periodic table, we see that it has 13 electrons on it. So if we look at our previous graph and we fill in those 13 electrons, we see that 2 would go into the 1s, 2 would go into the 2s, the next 6 would go into the 2p. That is used 10 electrons, 2, 2, and 6. I still have 3 more to go. The next 2 have to go into the 3s. I still have 1 electron left, and that has to go into the 3p. Notice that all of my s orbitals can only hold 2 electrons. It doesn't matter if it's a 1s, a 2s, or a 3s. They all can only hold 2 electrons. My p orbitals can all hold 6. So this one can hold up to 6 before I have to move to the next orbital. And this p, even though it can hold 6, we only have 1 electron left over to put in there. Now, if we were to look at all of the electron configurations for the atoms, when we look at aluminum, what we see is that the first part of aluminum is the same as what we see for a noble gas, neon, 1s2, 2s2, 2p6. And so sometimes what we do, especially for larger atoms, is we use something called noble gas notation, where we replace this type of a portion of an electron configuration with just the noble gas chemical symbol, atomic symbol. So we would write something like this: Ne, neon in brackets, and then 3s2, 3p1. So we would say this is the same as neon, and this is the rest of what I have in there. What we see out here are things called valence electrons. And the reason we're concerned about those electrons is because those are the highest energy electrons in the atom, and those are the ones that take place in all of the chemistry that an atom is involved in. These other electrons that are in here are called core electrons, and they're held too tightly to the nucleus to take place in any chemistry, and so we generally ignore them. Now, as we're moving across a period, okay, so a period is our left to right blocks of atoms in the periodic table. They're all going into the exact same n level. So they're filling in the 2s, 2s and 2p's, or filling in the 3s, 3p's, 3d's. So those all go into the exact same n level. When we move to a new period, we move one period down in the periodic table, we're moving into the next highest n level. So as we move from helium to lithium, we're going from the n equals 1 to the n equals 2. As we go from neon down to sodium, we're going from the n equals 2 to the n equals 3 level. And so the number of electrons in the highest n level, and that's really important, in that highest n level, so you have to look at it a lot of times in electron configuration for larger elements, number of electrons in that highest n level are called valence electrons. And again, we mentioned this earlier, they are the most important when it comes to bonding and also when it comes to reactivity. So let's look at an example of germanium. That's a fairly large atom there. We're going to write the electron configuration for germanium. We see that it has a Z value. So if you think back to our very first portion of this lecture, Z is often given for the atomic number, the number of protons. It's 32. We get that from the periodic table. There's a little 32 in that upper part on the periodic table. 32 protons means that for an atom of germanium, we will also have 32 electrons. So I have to find homes for 32 electrons, and we have to go in order. So the first two are going to go into the 1s. The next two go into the 2s. The next 6 go into the 2p. The next 2 go into the 3s. The next 6 go into the 3p. So notice at this point we have 18 electrons placed. We've got 2, 2, 6, 2, and 6. That adds up to 18. I still need 14 more places. The next one that goes in, as far as the lowest energy, is the 4s. That can still only hold 2. I've got to find 12 more spaces. Then the 3d comes. If you look at the 3d, it's got 5 orbitals. Each orbital can hold 2 electrons, regardless of what type of orbital it is. So the d shell, subshell, can hold 10 electrons. That's used up 30 electrons, and the next 2 go into that 4p. So that is my electron configuration for germanium. Now, if we want to know what the core electrons and what the valence electrons are, notice that my highest n value here is 4. I've got 2 electrons in the 4s, and I've got 2 electrons in the 4p. Those are my valence electrons. Even though this 3d shell came after the 4s, once it began filling in with electrons, its energy drops and it goes below the 4s and the 4p. So only the 2 electrons in the 4s and the 2 electrons in the 4p are considered to be valence electrons. And so germanium has 4 valence electrons. Okay, I mentioned earlier that we can use that periodic table to help us write electron configurations. The periodic table becomes a very important tool for writing electron configurations, so we don't always have to remember the order that electrons fill in. The last electron to fill in, or at least the last entry of your electron configuration, can be found by looking at where an element lies in the periodic table. Okay, we have blocks and periods in the periodic table. So if it's in the S block, which are in the first 2 columns or groups of the periodic table, then we're filling in the NS electron, where the N is equal to the period. The P block, which is those last 6 columns of the periodic table. Okay, that's a P block, and that fills in as NP, so where N is still the period. the D block. Now the D block comes in a little bit late because it comes in after the 4s, and so we have to subtract 1 from the period, from the periodic table. Okay, and those are the numbers on the left-hand side of the periodic table. They fill in as 1 less, and then the D. So when we're in the 4th period, we would actually be filling in the 4s, and then we're in the 4th period, so we take 4 minus 1, and we fill in the 3D. And I know this sounds really confusing right now. We'll see how it works in just a moment. For the F block, and we don't get into those too often, but you see them once in a while, then you have to subtract 2 from the period number to figure out which F orbital you're filling in. Okay, so let's do an example for chlorine. Okay, so for chlorine, we can do our noble gas notation. We see that chlorine is way out here. It's in period 3, so these are your period numbers out here. Okay, and so, and then we have our group numbers right in here, and these ones up here are very important. Okay, so we're going to start with neon, writing our electron configuration. Okay, so there's our neon, and then we see that chlorine, in order to get from neon to chlorine, we have to come down here, we have to pass through this one here, and so we're in period 3, and in blue here, this is our S block. We have to go through both of these to get to the chlorine, and so I have to fill in both of these electrons here. So that's going to give me a 3s2. Then I have to go all the way across here, and this is the P block in period 3. So we have n equals 1, 2, 3, 4, 5. So it's the 5th element of the P block in the 3rd period. And so we would write that as 3p5. So we could write this as neon 3s2 3p5. Let's try another one here, selenium, a little bit bigger. We see that selenium sits way over here. It's another P block element. It is in period 4, okay, and it's the 4th element in the P block in period 4. 4th element is 1, 2, 3, 4, okay, and so I know that it's going to end in 4p4. We're going to use noble gas notation here again. I'll change color here to blue. So we're going to go argon, and as we pass through, we've got to go through the S block again, and we've got to go through both of those S block elements, and so we're going to fill in both electrons from the S block. So we're in period 4, and so it's going to be 4s2. Okay, and after we pass through the S block, we now enter the D block. And we have to be a little careful here, because remember, in the D block, the value of the n that goes in front of the D is the period minus 1. We're in the 4th period, so 4 minus 1 is going to be 3. So this is the 3, and we have to go through all 10 of the D elements to get to selenium. So that's going to fill in 10 D electrons. So we're going to have 3d10, and then I've got to come over 1, 2, 3, 4. I'm back in the P block, and for the P blocks, our n value in front of the P is the same as the period, and I'm the 4th element over, and so 4p4. And if we look up at valence electrons, the only ones that are valence electrons is that 4s, the 4p, so I have 6 valence electrons. Okay, so you're going to want to practice some of these, and once again, if practicing them just doesn't seem to help you, and if you need some other ways of looking at how to write electron configurations, please contact me either through email or just come see me. Good luck.